Hello and welcome to my experiment 1. My name is Castillo from CPE108L, section E01. And today we're going to do the familiarization with the simulator, which is the experiment 1. So, for the first step, we launch the LCM simulator, which is this file right here. And this is the IDE. So let's set this to side by side. So click new, and then we encode the following programs. So org 0000H, we clear A, move A, number sign 19H, move R6. Now, the presence of letter H here in the and the number sign indicates that these are digits, hexadecimal digits, where in this case in our 1, 2, 3, 4, fifth line, this one is a decimal, while from the fourth line is a hexadecimal. So here we now have the end. So the first line that here initializes the starting address, which is at 0000 in hexadecimal. So to speed up the frequency on our step 4, we choose 1, we click save, and experiment 1 part 1. So any file name, then we click ASSM or assemble, and to assert the output we click run. So the accumulator was changed. Is this right? Move A. So the value in the accumulator was changed due to this move A 19H. A is the accumulator, and for the register 6, this is the line from program counter 0003. It stores a decimal value 09. So let me check if I'm recording. I'm recording. So, and we click pause, and to stop the execution we click reset and click assemble, but this time we're going to step. So the values here, so let me just set this all to 00. So let's assemble, and we step. The value in the accumulator was cleared. We step again, the value in the accumulator was 19 in hexadecimal, and we step again, the value in our register 6 is now at 09. So let's answer the this one. So I'm just gonna copy this. 6 is 0, x09. I'm going to change the one style. R0 is 0x19. So on to our next step. So assemble, we click reset, we click assemble, and we already did this step part. And to encode, edit, and debug, we click reset and add the instruction move R5, number sign 256. After move, I forgot to add the last code, which is move R08. So let me just do that again. If we click the run, so R0 contains the accumulator, so the value in the accumulator. So let's pause, let's reset and add the code that I deleted earlier. which is R5 256. So let's run. Let's see. Let's click save and let's just overwrite it. Yes, click yes. Assemble and then we run. So let's answer question 2. So if we analyze first here, on our R5, the value did not change. It's still 0x00. And if we look at our data memory, it contains two place values. And assuming we are using hexadecimal, which is the maximum is FF, or the value of it is 255. And if we store a value of 256, so it cannot be stored because it already exceeded uh, the limit. The out the output on our file did not change because the source being stored exceeded the limit of FF, which is 255 in decimal. Okay, so that's for question 2. So for our step 19 out here, we pause, we reset, and add the following into the encoded program. So after move R08, so here we add use register B to store 3CH. So we type to store, we type move B, comma 3, number sign 3CH, and store the sum in register A. So we have add A, which is a destination and our source. Store the result sum, add the contents of A and B, and start playing. So here we save, click save. Let's overwrite this one and assemble, no errors, and we run. So let's pause that. So let's answer that. Question 3. So these are the added. Let's just copy paste this for now. So these are the added instructions and the output of the program. So since we have so the output is the register B contains let's run. The register B now contains 0x3C, and the register A now contains, the accumulator contains 0x55, which is the sum when we add the value 19, hexadecimal 19 and hexadecimal 3C. So what will happen if the destination of the sum is changed to R0? So let's see. Let's pause and reset this one and change, since this is the destination in our addition operation, it changes to R0. And let's try assembling it, and we can see that there's an error. This is due to the uh, it will not build because R0 is a register, is a storage register, and the instruction add needs an accumulator register as its destination to store the summands. Yeah. Okay. So I will comment this with a semicolon and retype the original code. So let's save this one. And there. That's for our part 1. So let's see on our part 2. We click new. No, because we already saved it. And we reset the values 0 0 here. Okay, and click reset. Okay, we encode the following with the starting address. So to encode the starting address, we type org 0000h with a main semicolon clear A. To ensure that the accumulator is clear, move R5 number sign 35H, a hexadecimal number, move R7 number sign 45H, another hexadecimal number, move A number sign 0, a decimal number, add A, comma, R5, add A, comma, R7, add A, there's a typo here, there should be a comma, number sign 27, hexadecimal, and end of the program. So for step 3, we save, we use different file name, let's call this part experiment 1 part 2, and let's assemble and run the code. Let's try and increase the frequency, and let's pause it there. So we answer question 1.1. So let's see. So now assuming that this is based on the program counter, we can just step this one. So on our clear A, our accumulator start will be set as 0, and our R5 now contains 0x35, and our R7 contains 0x45, and our accumulator contains 0 0, so 0x00. Now for our first addition operation, so let's step. So here on our program counter 7, we execute, we have 0x35, so that is decimal 0 plus hexadecimal 35h. So I think the decimal will be converted to hexadecimal, and the values for the hexadecimal will be added. That's why we will get 0x35. And for our add AR7, so with existing value of 35, we add the 45h, we add the 45. So let's take another step. So the answer of that is 7a. So 0x7a. Now for our last operation, the add a, comma, number sign 27. So that is a direct addition. So step again, the answer is 0xa1. So let's type the answer 0xa1. So let's go to the board memory and complete the table. So let's see if we can look the program code. Okay. So I think the opcode is not present here, but we can use the documentation here. So let's just put this on the left, on the right. So if we look at our clear A, so let's just find that here. I think. Excuse me. So let's look for clear. The clear is okay. Here, clear A. So the opcode for that is E4, and the byte of instruction is 1. E4 CLR 8. So that is it. if we have move R5 immediate, so that is, it means immediate storage of the number, because the direct is used for the registers if we are storing register to register. So let's see. Move R5 number sign immediate. The opcode for that is 70 with a byte size 2. And see if there's any other things that I need to execute here. So let's just say that I answered this one. I finished answering. So in this video, I'm just going to execute all the things that are here. So let's just continue working. Okay, so then 7H. So let's reset, and I will add a comment to indicate that this is for different questions. For next questions, so uh, okay, let's see. So if we check, look, continuing on our step 7 of our part 2, if we check at our PSW, if we run this part, so let's run. Our PSW is now at 45. I think that's the last uh, digits that was, or that was the last value that was used in the operation, which is, so as you can see, R7 here. But uh, the last operation, R7 here, that is the last value that was stored in our register. So I think that's the purpose of that, the PSW, the last value that is stored on the register, because this on our program counter 9, this is the addition operation. So the uh, the hexadecimal 27 is not actually being stored in any of our registers, but rather it is being added on our accumulator registers. So that is for our step 7 of part 2. So now uh, let's see. So let me just pause the recording for now. So I'd like to correct myself after uh, searching about this. So this PSW, uh, not this one, but the PSW right here, contains all the carry flags. So if we look at the values here, so so we have a flag for AC. Arithmetic operations generates carry after lower half and send it to the upper half. So basically, if the first place value generates a carry, it will trigger, and then it will add to the next place value that is present. So we have a flag for AC, and this one, if we hover, this is OB. Now what is OB? OB, I think that is the overflow flag, and P is the even parity flag. When the result of even so it has even number of ones, then it will be one. So that is so. So let's answer this one. Uh, Total bytes is the number of instruction here. So let's see, AC this one. Let's see, RS1. 0. That's 1, 2, 3, 4. This is 1. This is 0. That is okay. Okay. So let's go to our next. So okay, so I'm instructed to create another file. Let's check if I'm recording. Yes, I am recording. So let's save this. Let's go this and we click new. Okay, so let me just load our existing and copy paste. So new, no, let's paste it and uh, can I just copy paste this one? Let's see. Yes, I can just copy paste it. Oh, for the formatting. So let's just delete all the comments. So okay, let's save this one. Let's just call it experiment part 3 ASM and change PSW to 18 inch. Okay. Age symbol 18. Let's say so. Let's turn this into 18 and let's reset everything else except PSW starts at 18. So, step. Okay, so let's answer question 5, table 4. So, okay, location. So let's. Oh, wait. So okay. So this is the memory. So we can get the address. So it here states 0x00. That is 0 and this double 0 right here. And if we want to get the location for the let's test this out. So if I want to choose and enter it with the value of 1 here. So okay, 00 start with 20. So let's analyze. So it means the 00, this is the first two zeros from the left are this one and the last 0 is from the top. Okay, so let's reset everything to what it should be. So 1, let's turn it to 0, and our 2, let's turn it to 0. So now, if we want to get our RAM locations, so we have 0x05. Let's see. Okay. So let's see. With our PSD 18. Wait, let me check. Okay, so I realized that I cannot change the actual PSW right here because it keeps turning on to 19. So let me just reset, and let's get the binary value of our 18, which is 00101 double 0 and 10. So I think let's reset this to 0. So that is wait, so in hexa, let me check. So it says hexadecimal 18. So let's see. We choose the hexadecimal of 18. So hexadecimal of 18 is right here. So let's use that. So 000. Okay, so we change our PSW to hexadecimal 18 properly this time. So let's run it. So symbol and run. Okay. Okay, I think that's enough time. So let's continue answering. So I think it did not change that much. So we still have our 0x05 containing 35, since that is in hexadecimal. So I'm not sure if I need to indicate that it is in hexadecimal, but I'll just put. Okay, so if we check our register 7, register 7 contains 0x07 contains 45. So let's try using 10, but on 8, let's see. Oh, 1, what? 1. Let's try 7 in 8. Okay, so the order of the address is uh, reverse. So instead of 10, you input it 0, 1. So that is how we do it, which is 0x18 contains a value of 50. In our 0x19, 0x19 contains a value of 60, and 0x1a 0x1A contains 70, and I think that's 5. 1, 2, 3, 4, 5. Is it only 5? Yeah, I think it's only 5. So I'm just gonna follow the format. Let's see. So for table 5, for table 5, this is for the PSW set to 10 hexadecimal. So 10 hexadecimal is, oh yes, 0001, binary of 1, binary of 0. So separated with a group of 4 binary digits, 2 groups of 4. Uh, so it's 0. So let's reset. So this is 10. So here PSW is at 10. We assemble and we not wait. So wait. Let me see. Let's try setting everything. And let's turn it to 18. So binary of 1 is 0001. Binary of 8 is, what is the binary of 8 again? 1000s. Okay. Let me pause my recording for a second. So I think I made a mistake right here. So let's reset everything 0. So let's set this to manually set this. Let's save this file or part 3 and load it. Let's see if it will. Oh no, so so let's see. Let's just okay to the let's reset everything. The 17, 18, 18, A, and D. I think F. I think. Why everything is reset? So okay, let's try again answering our table 4 with 18 and symbol and none. So now we have the actual values. So okay, so here we have, I'm just gonna move. Okay, so we have 0x1A, which is in register, contains 90, and 0x1F contains so that is our table 2. And for next let me just reset this one. So 00 19
Kain na kayo si Jane. Ah,
1F. Let's reset it. Okay, so for the table 5, I'm instructed to do PSW 10H. Okay, 10H, so 10 hexadecimal 10 is just this one. So 10, and everything is clear. Let's assemble, and let's so here you can see that the location moved to 100. So the starting address is now at 0x10, 0x11, 0x12, 0x15, 15, and 0x17. So with the same values there. So let's see. Okay, so I think that concludes my demonstration on the uh, familiarization of the EDS simulator. So we can see that uh, these are the commands or the instructions such as clear, move, add, and subtract. All of the operations move, add, subtract has the format of instruction, destination, comma, source, and if the operation contains arithmetic logic, then the resultant will always be stored on the destination. And for the accumulators, the addition instruction must always have the destination at the accumulator, and it cannot use the registers as its primary location. So if we want to store the resultant, we must get the we must store it first in the accumulator, and then from accumulator we store it to the register. So here uh, we can see the resultant here on this part. So the PSW is the index that sets the uh, flags, the carry flag, various types of flags, the accumulator flag, the reset flag, the parity flag, and it can also alter the data memory location. So instead of storing it here on address 0x00 with a PSW of 10H, so the 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 values are stored on the 0x10. So there. So here we have our opcode. So these are the machine language that uh, the microprocessor use. So I used the what you call this, the documentation for the opcodes for 8051 in hex. So it is very helpful. So with the number sign in imed means immediate number is being used, and direct is for the register. So uh, if the move uh, if the instruction contains any immediate numbers, it uses 2 bytes instruction. But if the instruction contains uh, existing registers such as the accumulators or the registers R0 to R7. It only uses 1 byte of instructions, and the size of instruction is also reflected on the ROM address. So starting with 00, so the starting instruction starts at 0, and then the next instruction starts at 1, meaning that the first instruction uses 1 byte of 1 byte size. So let me just correct this one. So this one uses 10 bytes. So counting this one, the start. So let's see. These are the carry flags, and this is the RAM locations, the RAM content, and all of which are reflected in the data memory. And let's see. So in the case where if you want to store value greater than 255 or in hexadecimal FF, we cannot store it. So let's say, for example, here in the experiment we have 256 that exceeds the two-digit hexa on our data memory, so we cannot store it. So it will just simply not stored on our memory. So okay, so I think that concludes my experiment one. So again, I'm Carlos Silva from CPE108L, section E01, and thank you for watching.